Okay, should be recording. Yes. Okay. All right. So, as I am apt to do, I have a picture this time, just to kick off the lecture, of a product that had, I guess, pretty neat, interesting, cool intentions, but very clearly from a functional perspective is a major fail. So hopefully you can see this. This is a bit of a blurry image. I can only find this in a low resolution form, but it's a coffee mug, right? And it's meant to be, kind of in the shape of a splat, right? So some liquidy stuff hits the ground and splat, and it makes this sort of splat shape. So very cool in terms of the manufacturing process, right? Somebody had to come up with this kind of splat shaped tool to make this cup in, right? So the cup obviously is some sort of porcelain or ceramic, and so it had to be like pressed between two splat shaped molds essentially and fired, and to get this shape. So somebody put a lot of time and effort and probably money into the manufacturing process to make this cup. And it's kind of a neat, cool collector's item, right? A splat shaped cup. It's kind of a cool thing. Except when you've got it filled up with coffee, the way that it's shown here, right? And here's the handle off to the right, which gives some suggestion of how this cup is meant to be used. So you fill it up with hot coffee, you grab it by the handle here, and you try to pour some coffee, sip some coffee into your mouth. And what happens?
It pours off to the side.
Yeah, right, exactly. All these little crevices here, more likely than not, probably cause the coffee to spill out of the side, one of the crevices, before you get a whole lot of it into your mouth. And if this is hot coffee, then ouch, right? Now you've got a McDonald's lawsuit on your hands. So anyway, so certainly as represented here, this cup would not function as a true viable coffee mug. It's again kind of a neat collector's item, but definitely a failure in terms of a cup that somebody could actually drink out of without getting themselves splashed with whatever liquid is that they're trying to drink. So again, just a kind of clever, interesting example of the designer not necessarily thinking about the end user, right, but designing something that he or she thought was super cool and marketable, which I agree it is. It's a very cool shape, but to actually purchase it and then use it as a coffee cup wouldn't work, right? As opposed to maybe purchasing it and just using it as a display. Maybe that would be its ultimate purpose. But to use it as a cup, it would definitely fail. So something interesting to think about. Okay, so today is our last of the prerequisite review refresher sessions. So we've talked about thermo, fluids, dynamics, and then today, and DML, and then today we're going to talk about Mech 1. And so Mech 1 kind of has a special place, at least in the reverse engineering report for this class, in that we're most interested in Mech 1 type analyses that involve failure modes. So we'll talk about a few kind of Mech 1 analyses that are failure related, and then a couple more that are sort of manufacturing related, but are related to the initial topic that we're going to talk about. But the thing that we want to focus on is seals, and this is not the Antarctic baby seals, but or the Singer seals, but I guess seal, there'd be one seal if we're talking about the Singer. But these are mechanisms that seal against fluid flow. And then just as a reminder, we're still talking about all of these kind of review and refresher topics in the context of the reverse engineering report, which is still due on the 24th. And you guys now, I think everybody has picked up their valves, and so are aware that we're reverse engineering a pressure relief valve, and hopefully have at least made a start on measuring some of the dimensions and thinking about how you might enhance some of the analyses that we've already talked about. This pressure relief valve contains a seal, which you could sort of see in this image. It's right here, right? So there's a some sort of an orange plastic polymer material, which is on the surface of the valve piston or poppet, as we're now calling it. So it's on the poppet, and then the poppet presses down. The spring presses the poppet down onto kind of this raised circular section here, which is the valve seat, and the soft material on the poppet deforms a little bit, and that deformation creates a seal that ensures that this valve remains closed. Well, at least for the pressures that you want it to remain closed for, right? Eventually, as we know, it'll open up to relieve pressure. But the purpose of this seal is to ensure that you don't get any unwanted leakage of the pressurized fluid inside the system out through the poppet valve until you actually reach that threshold poppet valve crack pressure that we talked about before. And that's when the pressure relief process starts. So in kind of thinking about how that seal works, I've got kind of 3 goals that I set for myself here in terms of doing my Mech 1 failure type analysis. So the first one is under what acute force balance condition will the valve fail to seal? The second one is how was the valve seat manufactured to facilitate sealing? And the third one is what is the expected long-term valve sealing failure mode? So 3 goals. Now, here's the part where hopefully the technology works. So instead of preparing, sort of conventional slides, I've just got a slide that has a big blank section here. And the idea is to just be able to sort of copy and paste a number of these blank slides and to be able to write here so that instead of just seeing slides, you guys can see my handwriting, and it puts a different cadence on the class. So this is the moment of truth, because this is the part where the computer crashed last time. And like I said, if I'm using a different computer this time, different hardware, and so this should be okay. But if it's not, and I crash for some reason, we'll come back. And I do have a Doccam. Let me see if I can show you that just for interest here. So there it is. So there's my hand, right? So if this mode fails, I can just bring a piece of paper under the Doccam and I can scribble stuff on the piece of paper, and hopefully I'll write it big enough and dark enough that you'll be able to see it. But let's try to do the the technology one more time, see if we can get it to work. So but if I crash again, oops, there we go. Okay, if I crash again, I'll just jump back in, and then we'll go to the Doccam instead of trying to kind of beat the dead horse of the digital technology. Okay, so this is going to take a little of me getting used to. Let's see. Well, it was working before. Okay, so I can do it there. Oh no. Dear God. Okay, well, it's a good thing I have a backup plan. So I'm actually trying to write with the pad and nothing's happening, which is not good. I've got it plugged in. Okay. It is kaput. Weird. Okay, that's funny because it was working literally 15 seconds ago before I started recording, but now of course that I'm recording and I have to do it for real, it's going to die on me. So this is why I have a backup plan. So let's go to the backup plan, which is the Doccam. So as I get that set up, my first goal out of these 3 is to get this out of the way, is to figure out under what acute force balance conditions the valve will fail to seal. And I'll kind of explain what all these terms mean as I transition over there. But let me close this down and open this up. I'm going to try to do this with a, let's see, there we go, with a black Sharpie so that it's easy to read, because I've tried this in the past, and students sometimes have trouble reading what I write. So I try to write really big and in a big black pen. Okay, so let's just talk about seals in general, and we'll start with types of seals. Okay, is that big enough? Can everyone see that?
Is it possible to zoom in just a little bit?
Yeah, I could try that. Ooh.
Yeah, thank you.
Yeah, that's good.
Okay, great. Okay, so we're on types of seals. So there's a whole bunch of different types of seals, and I'll just name some off. So I've got types of static seals. So these are seals that are involved in processes where none of the parts are moving relative to each other. And examples of those include things like O-rings and gaskets and a face seal, which, by the way, is what we've got. So this is our pressure relief valve. Has a face seal on it, which is the one that we're about to talk about. And then there's also various types of sealants. And so sealants include everything from like pipe glue to Teflon tape. And Teflon tape is used to seal threads, which is precisely what we have in our case. Because if we look, so let me switch here between this view and this view for a second. Let's see, did that work? There it is. Okay, so we've got two types of kind of sealing surfaces in our valve, right? So we've got the face seal, which is here, which is what I'm going to spend quite a bit of time talking about today, and then we've also got a thread seal, right? So this valve has to seal against something in the high pressure system at those two locations for it to actually successfully hold pressure. And so just as a quick aside, in talking about kind of sealants and Teflon tape, you would wrap the Teflon tape around these NPT threads, and then you would screw the threads into, so these are male threads, you would screw the male thread of the valve into the accompanying female thread in the fitting of whatever high pressure system you're trying to attach this to. And the Teflon tape itself actually deforms and fills the spaces in between the threads. And with the advent of the NPT, that tapered thread that we talked about last time, enough of the pathways for fluid to, get out between the seals end up getting blocked by the deformation of the Teflon tape, filling up all those void spaces, and you get a good seal. The face seal works in a slightly different way, right? Which is I'm using this spring to kind of push this deforming surface, this plastic deforming surface against a much more rigid surface. And I'm reliant upon the deformation of the polymer, the plastic material in the seal to deform to the point where enough pressure is required to sort of squish around it or move around it that the fluid doesn't have that much pressure to bring to bear. And so the seal is maintained even though the fluid is at relatively high pressure. It would take an even higher pressure to deform that plastic material to get the fluid to leak around the seal. So that's how those work. So those are our static types of seals. And then we also have dynamic seals, which include things like piston rings, so for example, an internal combustion engine has a series of piston rings that keep the piston sealed against the high pressure and high temperature combustion process. And then we have something like a lip seal, which could be used on a rotating shaft. So again, dynamic seals, which involve the motion, the motion of parts relative to each other, and the need to maintain a fluid sealed within, some sort of compression, some sort of pressurized compartment, despite the fact that I have, different elements moving against each other. Okay, so all of these seals, regardless of whether they're static or dynamic, basically operate in the same way. So all seals operate by filling a void space and eliminating flow paths. Between or through mechanical deformation. So in the case of the NPT threads that we were just talking about, so I've got my threads. So those are my male threads, and then I've got kind of a conjoining set of female threads that come in from the other side. And I now got this Teflon tape that's sort of in this space between the threads. And by tightening down on the valve, because remember these threads for NPT are tapered, I'm pushing the Teflon tape, like smushing it closer and closer and closer, and actually kind of forcing it to fill in all the various little holes and crevices and gaps that exist in the space between the two threads. And eventually, once I get this thing cinched down enough, all those different possible flow pathways and void spaces are all eliminated as a result of literally the mechanical deformation of the Teflon tape to fill up this space. So that's just in general, how seals work. Okay, so given sort of this qualitative sense of how seals work, can we start to try to quantify, to understand, and to calculate, a potential failure mode for our system? So the pressure to seal, which I'll call P sub seal, is just some force over some cross-sectional area. And in our case, the force for this is now, so now we're talking about the face seal. So the force is supplied by the preload on the spring, which we talked about last time or a couple times back, right? So that's F equals minus K delta X, where delta X is the preload distance between where the spring actually is when it's sitting in the housing in terms of its deformation, and then just the natural length of the spring when it's not sitting in the housing, right? So that's going to induce some force with, which I think now you guys have got, we've posted on Canvas the K values for the various springs, at least the raw data from which you can derive the K values. And so knowing those K values for your particular spring, and then the delta X, which you can get from measurements, or I think the value that I suggested was something like 0.9 centimeters, at least that's what I measured. You could figure out what the force is, this preload force that the spring produces on the valve seat. So that's our force, which I think you now have means of calculating. The hard part is the area. So how do we find the area? And the area, it turns out, is sort of the combination of two geometries. So if I think about kind of the contact, I'm going to have, and we're going to kind of keep this a little simpler than the actual geometry, just to make it kind of more clear. So I've got, in our case, I've got a kind of plastic deformable surface that's pushing up against a non-deformable brass seat. And the way that I'm going to kind of show you guys the derivation and the math is I'm going to flip those two around. So I'm going to make this surface, which for our valve is deformable, I'm going to make that rigid. And then I'm going to make the piece that for us is rigid, I'm going to make that deformable. And kind of leave you guys to think just a little bit about, how you might switch from rigid to deformable and deformable to rigid when you do your own analysis. But this is, so think of this more like an O-ring seal, right? Just as an example. So there is one of the two dimensions that we need, right? So we're going for area. One of the two dimensions that we need is this contact, and that distance, for reasons that will become apparent later, I'm going to call that 2A. So the number 2 in A, I could call it just A, but as we'll see later, the math works out better if you call it 2A. And so what I've got then is I've got a width of 2A, and that width of 2A has to become an area, has to basically be in contact all the way around what's effectively a toroidal shape. So if I take this kind of circular cross section and I project it all the way around, so we're looking at now half of a toroid. So I projected it all the way around so that it's half of a toroid, and then I look at the distance from the center of the toroid out to the center of the circle here that makes up a cross section of this toroid. I'm going to call that distance phi. So that's phi. And my area then is 2A. So this width of contact here, and then multiplied by the circumference of this full toroid, right? And so we know that the circumference in general for a circle is 2 pi, and in this case it's phi instead of r, so 2 pi phi. And so to kind of finish up and bring things together, this area is going to be 4 pi a phi. So that's now my total contact area. Okay, so I can now take this pressure that is my sealing pressure. So sealing pressure, and I can say that the force is minus K delta X, K delta X from the spring, and then divided by this sort of sealing area that I calculated, which is 4 pi a phi. Okay, so so that's pretty good. There's one more thing that I need to figure out though, which is what is this A, right? So what is A? I don't, from kind of this model of a deformable toroid of circular cross section, I don't have any good way of calculating A. So we have to then go to Hertzian contact. Have you guys talked about Hertzian contact in any of your other classes? It might have been a physics class.
I don't recognize it personally.
Okay. Well, then this will be a good brief introduction into Hertzian contact. So Hertz was a guy who did his work in and Hertz, by the way, the same. We use Hertz as a frequency, right? So it's like a dimension of oscillation. Same guy, right? Named after the same person. So in addition to doing a bunch of wave analysis, he also looked at contacts between surfaces, and this was in the late 1800s during kind of the middle of the industrial revolution, when things like ball bearings rolling over ball bearings rolling over surfaces, that was a big deal, right? So if you had a ball bearing and you didn't know the contact between the ball bearing and the surface it was rolling over, you could end up destroying the ball bearing, destroying the surface, not getting the kind of fluid motion that you like. And so Hertz did a lot of work on trying to figure out what that contact was between ball bearings and other surfaces of industrial interest. And so the place where he started was to look at a pair of spheres. And these, of course, look like circles. And the way that I'm going to denote them as spheres is I'm going to make my little Escher little reflection there, just to show that they're spheres, right? So that's this little shape is meant to be the reflection of the light off of the sphere. So we've got sphere 1 and we've got sphere 2. And Hertz asked the question, well, what is the contact between these two spheres look like? So just qualitatively, what do you guys think that shape looks like? If I've got these spheres and I'm kind of pushing them together with a little bit of force, so I'm pushing down on this one and I'm pushing up on this one. What does that contact shape look like?
A circle?
Yeah, exactly. Yep. So it's a circle. So it's a circular contact. And hang on, let me grab the next sheet of paper here. So we've got a circular contact, and so Hertz then gave us a couple of sort of values that we're going to use to begin calculating this area A. So the first one that he gave us is called a composite radius. And we'll get back to that contact shape being a circle here in a second, but it won't make any sense unless I introduce these other couple of things. Okay, so composite radius, according to Hertz, is 1 over r prime, and that equals 1 over r1 plus 1 over r2, where r1 is the radius of sphere number 1, and R2 is the radius of sphere number 2. And so this R prime value, this composite radius, is going to go into an equation that I'm going to show you guys here in a second. So that's one thing that we need. And then the other thing we need is called a composite modulus. And a composite modulus arises from the fact that we might have our two spheres that I drew before. Our two spheres might be made up of two different materials, right? So this one might be material 1, this one might be material 2. And so we need this composite modulus to kind of write an equivalent Young's modulus for the two spheres in contact with each other. And so the composite modulus is a little bit more complicated than composite radius, but it goes like this. So I've got E prime, and then that equals, and probably don't jot anything down until I finish writing because this is a bit involved. So I've got 1 minus the Poisson's ratio squared of sphere 1 divided by the Young's modulus of 1. And then this is plus 1 minus the Poisson's ratio of material in sphere number 2 divided by the modulus of sphere number 2. And then all of that lives in the denominator, and the numerator is just 1. And so just to be super clear, my E sub I, that's the modulus of material I, and then nu is the Poisson ratio. Poisson, I might say poison there. Poisson's ratio of material I, which if you know those materials, you can look up those values for E and nu, and then plug them in and get the composite modulus. Okay, so we've now got almost everything we need, with the exception of the equation for A. And so in our case, so I described before that all of this is sort of built up for two spheres in contact with each other. And the equation that I'm about to write for you is actually the equation of not two spheres, but instead two cylinders. So we've got a cylinder like this, and then we've got another cylinder like this, and they're in contact with each other. And that contact surface is, instead of a circle, which is what we talked about before for two spheres, for two cylinders, the contact is a rectangular shape. Rectangular shape. And that rectangle, perhaps is no surprise, has got this same area that we were talking about before. So it's going to be 2a. It's actually 4a. Let's try that again. 4 pi a phi, right? So that's our contact area between these two guys. Now there's a little bit of a trick here. Oh, well, so let me give you the equation, and then we'll talk about the trick. So the equation for the contact between two cylinders for this unknown A, right, which we're still hunting for, is the following. So A is equal to 2 times the force, and that's the force that has to be imposed from the bottom and the top to get these two cylinders to kind of squish together and to form into the seal, multiplied by the composite radius. And then in the denominator, we've got pi L and then E prime, which is the composite modulus, and all that is taken to the 1/2 power. So that's our value for A. Let's see, we're on page 3. Just keeping the pages numbered so I can keep track of where I am. Okay, so we've got this equation for A now, but we need a trick, right? We need to do something, because remember, we've got the equation itself is for two cylinders that are touching each other. And it's not too hard to imagine that those two cylinders touching each other could be just modeled as kind of two, toroidal annuli that are, just touching one another in contact and then being forced from the top and the bottom with this force F. So that's not too big a leap. The question is, one of these is definitely a toroidal surface, right? That for us is, this circular shape that for us represents the deformable element in the valve seat. The other shape is not a cylinder, right? It's flat. It's, if I go back to the original drawing, let's go back here to the original, right? So now we're talking about this surface on the valve piston, the valve poppet, which is flat. It's not another cylinder that's rolled up. It's definitely flat. And so how do we get an expression for R prime, this composite radius, if instead of having kind of two cylinders wrapped up as toroids then pushing against each other, now instead we've got one toroid, and then that toroid is sitting on a flat surface, and the toroid is being pushed down and the flat surface is being pushed up. So any ideas? Remember the composite radius equation is here. Let me give you a hint to start out with. So remember, Before, when we were doing it for spheres. So R1 is the radius of sphere 1. We're now in the world of cylinders. So R1 is the radius of cylinder 1 or toroid 1. And R2 is the radius not of sphere 2, but of cylinder 2 or toroid 2. And remember, we've got one toroid and then one flat surface. So how would I would describe R1 just as the radius of cylinder 1, which is the first toroid. What about R2?
Infinity
Yeah, there you go.
for the
Perfect.
flat plane.
Exactly. Perfect. Yep. So if I go back to this image, right, this is my R2. If I now just make R2 infinitely big, right, it basically just unfolds or unwraps the cylinder until it's effectively just a flat plane, right? And definitely from the perspective of cylinder 1 or toroid 1, toroid 2 with R2 equal to infinity is just a flat surface. And so yeah, that's exactly right. So I can, let me grab a new sheet of paper here. That was page number 3. So I can write now that for a cylinder pressed onto a flat surface, my composite radius 1 over r prime is equal to 1 over r1 plus 1 over r2, but r2 is equal to infinity. So that's because it's a flat surface. And if I then say, okay, this is now instead of 1 over R2, this is 1 over infinity, this whole term 1 over infinity, that goes away to 0. And so that just leaves me with R prime is equal to R1. And now I can write my A is equal to 2F R1, right? This used to be R prime, but now it's R1 divided by pi. What's this L? Well, that's the length all the way around the toroid, right? So that's going to be, let's see, 2 pi phi, there we go. And then multiplied by my composite modulus. And then I got to take the square root of the whole thing. And that's it. So now that's my value for A. And now remember, I can go all the way back, right, to my original equation, which I think was on page 2. Yeah, there it is. So my original equation on page 2 for P of the seal, and I can now plug in everything, right? Because I've got everything figured out. I've got an expression for A in terms of a force, which I can determine from the force from the spring. I know R1 because I can measure the size of the valve seat. Pi's and 2's are constants. This guy is just the radius of the major radius of the seat. And then this modulus I can get from my composite modulus equation, which is right here, just by knowing the properties, right? And you guys, if you have not been able to do so yourself, we've got a bunch of properties and data to determine properties of the various components now posted up on Canvas. So you should be able to determine based on things like density, spark test, flame test, magnetization, what the materials are that make up the various components of the valve, look up the elastic modulus for those parts, plug that in, and then get the composite modulus. And so it does take a little bit of kind of turning the crank, plugging and chugging, but there is now enough information to determine what that pressure is that will be the failure pressure for this valve. So that was, if you remember, that was goal number 1. Under what acute force balance condition will the valve fail to seal? So you guys can go through and you can calculate, for example, a spring stiffness, for example, right, a K value for which this force will not be enough to cause the valve to seal. for pressures that are lower than the cracking pressure, for example. So that would be, one type of Mech 1 failure analysis that we might be interested in seeing in the RER. Okay, so let me just pause there and ask if anyone has questions up until this point. Oh, good so far. Okay. All right. So we got just a couple of minutes left. And so I wanted to just spend a moment or two talking about the other goals, which is how was the valve seat manufactured to facilitate sealing? And for this one, we're going to have to go back to, okay, back to our white light interferometry. So let me bring the slides back up. Okay. So there we go. All right. So goal number 2 was how is the valve seat manufactured to facilitate sealing? So this is that same white light interferometry technique that we showed you before when we were looking at the surface finish on the hex shape on the outside of the valve. We also did the same testing technique on the valve seat, right? So this little piece of brass that sticks out here and facilitates this sealing that we were just talking about. And this is what it looks like. And so just like before with the hex having striations in a particular direction, this one also has striations associated with it. And they are, let me see if I can draw this. They are, you could see, for example, like right there. There's another one that's pretty apparent that's right there. Another one that you can see that's right there. So these guys look very linear, but it's because we're just looking at one little section of this seat, right? Remember, this seat is actually a toroidal shape. And so what we're looking at are these striations that sort of go around along the axis of the valve seat. So given what we know about striations from before and our discussion of kind of how valves seal from today, any kind of guesses, comments, thoughts about why these striations go in the direction along the length of the valve seat, as opposed to, let me grab a different color. So as opposed to like, that way, or as opposed to being circular, like you would expect to come from an end mill. So why did whoever picked the manufacturing process pick a process that gives us striations that are lengthwise all the way around the valve seat?
Well, if the striations were perpendicular to what it touches, wouldn't that give a path for fluid to get through?
Exactly. Yep. Exactly right. Yeah. So either case, right? So if I've got perpendicular paths, I should have drawn them in different colors. If I've got the red perpendicular paths, that's a very easy pathway from the pressurized side of the valve seat to the non-pressurized side of the valve seat. And I would have to make sure that whatever my seal material is basically sticks into all of those little grooves and striations and fills them up completely to prevent any gas leakage, right? So that's a very hard geometry to seal. And the same is true for like an end mill, like a circular type path. There's all these different places where the striations are overlapping one another. And so even though the path would be, pretty tortuous, it still is possible to imagine a pathway where you've got, something from the high pressure side to the low pressure side that isn't sealed by the deformation of this valve seat. But if I select a manufacturing process where the striations are all in line, as I've drawn them here, with the direction of the seat, it doesn't matter, right? Whether these guys are contacting high pressure, low pressure, or what, because there's no pathway out of the valve seat from the high pressure region to the low pressure region to conduct flow. So I've just got to make sure that the pressure is enough to just deform the valve seat to form the valve face, so that it just, kind of fills in. Let me see if I can draw it here. So it just fills in. So imagine I'm now looking at a striation kind of sideways, right? So this is one of these black lines now kind of blown up, right? So instead of having to fill it up completely, which would be the case for either of the options that I've drawn in red, instead now I just have to come along with my valve seat and just have a little bit of deformation like that. And so long as I've got a good seal there and a good seal there, that's it, right? That's all I need. As opposed to having to fill up this entire space and make sure that it's sealed all the way through. So when you guys go through and sort of think about the manufacturing of this part, note that because we have this scattering white light interferometry image, and we know that the striations are running kind of lengthwise around the circumference of the seat. Think about how they would have manufactured this feature, knowing that the striations are in that direction, right? It was not somebody coming down with an end mill and actually polishing the surface, because that would have left circular striation marks as opposed to the linear ones. So that's at least a little bit on goal number 2. So any questions or thoughts on that one? Okay, so we've got just about a minute left. And so then goal number 3 is to address the expected long-term failure mode for valve sealing. And in order to sort of think about this one, whereas in the previous slide, we were imaging the metal, I'll call it brass-like material of the valve seat. Here in this last slide, we're now imaging using that same white light scattering interferometry technique, the plastic side, the side that actually deforms, which is the polymer that's adhered to the poppet valve. And what you can see here already, right? This has not gone through a huge number of cycles, because I think none of these were actually used in practice before we slice them open and image them. But already you can see this big sort of divot, right? There's this big purple splotch in the middle of this surface, and that splotch represents a hole, a cavity, a divot, like I said. And that just comes from the fact that even over just a couple of cycles that this thing has gone through with somebody just messing with it, that polymer has deformed to the point where this divot is basically permanent, right? Because this thing was taken out of the valve and it was imaged without any, sort of valve seat or anything attached to it. It was just the, undeformed polymer that we were looking at, the unforced, unpressurized polymer that we were looking at, and it already has this divot built into it. And so one possibility, at least, for how this thing might fail is if I come along with, here's my metal brass-like, sorry, I don't want to give up too much, brass-like seat. And then I've got my now relatively soft but deformed material associated with this polymer on the valve poppet, and I bring that material down. Let me see, can I grab it? Or is it going to let me do that? Come on. Maybe. There we go. Okay, I grab it and I bring it down. It's going to stop where that first contact happens, right? But what's happened is, instead of having this, really big, so remember before we were talking about the area of contact being 2A. So instead of having this really big contact area of 2A, I've now got this really tiny contact area where just this corner of the solid piece is in contact with the now deformed soft material associated with the valve poppet. And I'm going to get a leak, right? Because the force isn't strong enough to produce a good enough seal to prevent the gas or fluid or whatever it is from getting through. And so given that we already see this deformation, even for a valve that hasn't even gone through, an industrial number of cycles, it's gone through, just a handful of cycles as we've been demonstrating, and we've already got this divot, this deformation. This is one possible failure mode, and the one, at least, in the absence of additional information, the one that I would expect to cause a long-term failure of the valve. So that's something to think about for, again, a Mech 1 type analysis. How many cycles is required to get this thing to deform to the point that it no longer seats properly and then causes a leak? Okay. So let me stop there, because I know we're over time. It's 3-day weekend, so I want to be sensitive and give everyone a chance to go off and have their happy Friday afternoons. But let me stop there. And just quickly ask if anybody has questions about anything we've talked about.
I have the poppet in hand right now.
Yep.
From the disassembled one, and it seems as though there's like a circle already like formed inside.
Yeah.
So it's not from like testing it or anything. It was just built in like that.
Well, so I don't know that it was built in like that, but I imagine when they coated that polymer onto the metal surface, that feature that you're seeing wasn't originally there, right? I don't think they put that there on purpose.
Oh, okay, so it wasn't intentional. It wasn't.
No, but it's there because the valve sat on the shelf for some period of time, right? And the spring was forcing the poppet into the polymer, and the polymer very slowly over time was deforming, maybe even flowing a little bit, right? Maybe it plasticized and flowed a little bit like a fluid, and now has assumed that shape that you see, in the surface in front of you. But I don't know that it was intentional. I think it's just a result of these valves, sitting for a period of time with those springs engaged and causing a plastic deformation of that surface.
Oh, okay, thank you.
Sure. Any other questions?
I have a question regarding like taking some measurements and stuff.
Yeah.
So like when we get to the point where we got to CAD like the inner stuff of the like the housing where the brass seal is, can we like come to the lab and take measurements off the cross section ones, or get one of ours cross section, or do you kind of provide those or something?
Hang on. So do you not have a cross section one?
No, I have one that's in pieces but not cross section.
Oh, okay. I gotcha. Okay. Sorry, I was thinking about something else. Yeah. So we've got a couple of them that are cross section. So there's two possibilities. So you guys are, I'm getting an echo of myself here. You guys are in the online section, and so there's sort of an underlying assumption that you're not physically able to come to campus. If you are physically able to come to campus, that's awesome. Come, we're here Wednesday, starting at 9:30. You guys can come to open lab hours, and you can do everything that the in-person students are doing. If for some reason you cannot come to campus, we're going to have a virtual window open, and Ezzy, who's one of our fellows this semester, is going to be kind of in charge of the virtual open lab hours. And you can ask her to, if you need a particular section cut or you need a measurement taken of some kind, she can actually do that for you. So she's meant to be kind of your eyes and ears in the lab and your hands in the lab, if you guys can't physically be here. So you have two choices. You can come and do it yourself, or you can ask Ezzy to take those measurements and relay them to you.
Okay, good to know. Yeah, I can make it to those lab hours, so I'll probably just do that.
Great. Okay. Sounds good.
Thank you.
Sure. Anything else? I'm gonna stop recording.